This is 2007, AP question number 4. Let's read it. Investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacteria contamination in beef. 2 different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens of a certain type of beef. So I think the thing to pay attention to here is this statement. So you can see that you have sort of two rows of information here. And one of the things you're going to have to do in these kind of questions is decide, is it a 1-sample test or a 2-sample test? Are you comparing 2 different groups, or do you have one group of specimens? And when you look at this question, all right, so just so we're clear about that, so for example, if you look at this number 5, this refers to the 5th specimen of beef, and this is the E. coli result from test A, and this is the E. coli result, from test B. So what you're doing is you're performing 2 tests on each specimen. That sort of lets you know that this is a match pair experiment design. Okay, so you should think about that. Is there a significant difference in the mean amount of E. coli detected by the two methods for this type of beef? Provide statistical justification for your answer. So let me warn you, as soon as you see this question, is there a significant difference in the mean? Something like that. That simple little question means you have to do a whole significance test. Okay? So you need to state your hypotheses and so forth, and all the work that goes. So we'll notice in this case that we don't know sigma. Sigma is unknown. And since sigma is unknown, that implies we're going to have a t-test. All right? Specifically, a 1-sample match pairs t-test. So whenever you do a problem like this, you need to indicate what test you intend to perform. Okay? And now we need to define some variables. So we're going to let mu equal the average or mean difference in E. coli levels detected by the 2 tests. So we need to decide an order. So let's say we decide we're going to do A minus B. We're going to do the level of detection of E. coli by test A minus the level of detection of E. coli by test B. Once you define mu, you can state what HO and HA are. So HO and HA. So we're going to let mu HO equal, or B mu equals 0, and that indicates that there's no difference in the amount of E. coli detected by the 2 methods. Okay? And then if we think about HA, it's usually mu is greater than, less than, or maybe not equal to. We need to decide. And to do that, you should go back and reread the question. So look at the question we're being asked. Is there a significant difference in the mean amount of E. coli bacteria detected by the 2 methods? So there's no direction of a relationship being suspected. They're not saying, does test B detect more bacteria than test A, or vice versa. So your HA in this case is that mu does not equal 0. So that means we have a 2-sided test, and it's good to make a note of that. So now, with any test, you need to write down your assumptions. So first, we should have had an SRS, and they did say that. If we go back up here in the language, 10 randomly selected specimens of a certain type of beef. So that takes care of the SRS part. You want the population to be greater than 10 times your sample size. Or in our case, that would be 100, because n is equal to 10. And certainly, there are more than 100 specimens of beef that could be out there to be subjected to E. coli. We call that the test for independence. Okay, and while we're at it, let's make a note that S of x bar is going to be S of x over the square root of n. So we know that we're going to use this as our standard error. And a t-test problem, we don't call this the standard deviation of the sampling distribution. We call it the standard error. Okay? And then lastly, the last check is for normality. All right? So n is only 10 in this case. So we're going to have to check our box and whisker plot, and we're going to have to check our normal probability plot for the differences, and hope that we've got a nice linear normal probability plot, and then we also have a symmetric box and whisker plot. So let's go to our calc. So we're going to go to stat edit, and we need to make some decisions. So in list 2, for example, maybe I'll put specimen B, and then in list 1 I'll put the corresponding, the same specimen but with test A. So let's go get that data and plug it in. So magically all data has appeared in these lists. We're going to go over to list 3 now, and on the top of list 3 we got to just pick the order in which we're going to subtract. Now we defined our mean to be the mean for A, the test results of A, minus the mean test results for B. So I'm going to do second list 1 minus second list 2. And you should be used to subtracting, 2 lists when you do a match paired t-test. Okay? So we notice it looks like, in general, test A is reporting higher numbers because a lot of these differences are positive. Okay? All right, so now we need to check for the normality of list 3. So to do that, you do second stat plot, and second y equals. All right, so here we go. I already have the normal probability plot selected, so I'm going to go with that. I'm going to go zoom 9, and here we go. And this is promising because that graph looks pretty linear to me. So we can see you could draw a pretty straight line for it. So the normal probability plot is approximately linear, and that implies that our data are approximately normal. So that's a good thing. Now we should go and check a box and whisker plot and hope that we don't have any strong skewness or anything like that. So hopefully that'll happen. So we're going to go second y equals again, and we're going to select the 4th type of graph, which is a modified box plot. It will show us outliers if we need them. Here we go. Zoom 9. All right. It's not perfect. I would call that moderate or weak skewness. Okay. So we have, I'll just say moderate skewness. Okay. And so we might say safe to proceed with T procedures. Honestly, with an N of only 10, I would have preferred if this thing were a little bit more symmetric, but it's not terrible. Okay? So let's go back to our test and not forget what we're trying to do here. We're trying to test the hypothesis that mu equals 0. The mean difference between the tests is 0. Remember, we did A minus B versus the alternative that mu does not equal 0. Okay, so to do that, we need to draw a picture and calculate a T-test statistic and so forth. So T equals x bar minus mu over S of x over the square root of n. This is called the T-test statistic. Okay? Now, you'll notice there's lots of things in here we don't know right now. We know mu equals 0, but we don't know x bar. We don't know S of x. We do know n. We know that's rad of, 10, and then hence the rad of 10. But to get these things, so these things are in list 3. We can find them. So here we go. We do stat, calc, one variable statistics, list 3. Okay, we hit enter. And you have an x bar of 0.29 and an S of x of 0.629, or really 6.3 when you round it. So 0.29 for x bar, 0.63 for S of x. So we can plug those things in, 0.29 and 0.63. And now we're ready to calculate our t-score. Okay, so here we go. 0.29 minus 0 is just going to be that, divided by, open parentheses, 0.63 divided by the square root of 10. Close parenthesis. Oops, I pressed the wrong button there. I meant to press square root. That's annoying. So let's do this. I've got to fix this. Great. So 0.29 divided by the square root. That worked. Oh, that's not even right either. Great. Enough mistakes. 0.29 divided by, open parenthesis, 0.63. All right, that looks promising. Divided by the square root of 10, close parenthesis. Oh, let's get out of that. Hold on. I keep making that mistake. Get out of that thing. Close this parenthesis, and now the whole denominator is closed. Okay, finally. So our t-score is 1.455, or 1.456, really. All right. All right, so we're ready to draw a picture here. So here's our t-distribution, which looks like a normal distribution, but we know it's really not. We know it's a little bit wider and a little bit shorter. U equals 0 in the middle. And we have a t-score, a t, that equals 1.456. Now, be careful. This is a two-sided test. Alternative hypothesis is not equal to. So you have to know that you have to go and make another t-score like this, symmetrically. Okay? And now our p-value is going to be the sum of those two areas. So this is a p-value, and over here is part of the p-value. Together, they add to the p-value. By the way, these t-scores correspond to an x-bar of 0.29. And over here, this would obviously be x-bar equals negative 0.29. So we need to make sense of this t-score of t equals 1.456. All right, so the first thing you should remember, if n is 10, then that tells us our degrees of freedom is 10 minus 1, or 9. So now what you do is in your t chart, you look in the degrees of freedom column, and you look down, you find 9. Okay? And then we're going to look across until we find those t-scores. Well, if I look across, what I'll notice is at some point I run into a t-score of 1.363. And then next to it is another t-score of 1.796. Well, our t-score is in between there. All right, I must have looked at the wrong column. Well, you'll have to bear with me. Plenty of mistakes today. All right, so t equals 9. Oh, there we go. 1.383 and 1.833. That should be better. Okay. So then t equals 1.456, I believe. So our t-score is between these two things. What you do now is look up to the top of the chart, and you'll see two numbers up there. Okay? You'll see a number of 0.10 and another number of 0.05. Okay? These numbers here are tail probabilities. So what that tells us is that the area in this tail here, that area, is between two numbers. It is less than 0.10, but greater than 0.05. That's what we're learning from this t-chart. And we also know the same thing about this area, too, because it's symmetric. So now we're ready to say something about our p-value. Our p-value, then, would be between, right? We think about it, just one tail by itself is between 0.10 and 0.05. If I had two tails added together, then that would be between 0.20 and 0.10. So now what can we say? Well, if we're going to use alpha equals 0.05, which is the typical significance level, then our p-value is greater than 0.05, and that implies that we cannot reject HO in favor of HA. And you should also write a sentence, I'm not going to write it here, but you should write a sentence in context. We can say that we did not find evidence that there's a significant difference in the amount of E. coli detected by the two tests. That's what it would mean to interpret this result in context. Now, I should show you one more thing. Just back to the calculator for a minute. If you go to stat and you go over to tests, the first one is the z-test. You'd use that if you know the standard deviation of the population. But the second one is the t-test. And that's what we use when we don't know the standard deviation of the population, like our problem. If you hit enter, you're going to see a lot of familiar numbers. Look at that. Okay, notice x bar is 0.29, s of x is 629. There's n. Okay, the only thing we need to fix is the alternate hypothesis. We need to make that not equal to. Every time you do one variable stats, the calculator automatically fills this information for you. So then we press calculate, and notice what you get. Here's your t-score. I should highlight this thing and grab it, because it's just too nice to look at. So notice there's the t-score that we had. And look at our p-value. It's 0.179. Well, that's definitely between the 0.20 and the 0.10 that we thought was going to happen. We made a mistake there. Okay, so that occurred. There's your 10, in case you forgot about it. There's your x bar. It's all there. And if you want, one more thing you could do. If you go to stat test again, and you go to t-tests, when you go down to the bottom, you can even have it draw the picture for you of the t-distribution. So that's sort of nice. This is where you'll know you have your picture correct. Oh, I forgot to turn off that box in Whisker Plot. But there's your t-distribution. And you can see the p-value shaded in on both sides.